Okay, so in this video we're going to start Unit 4, which is over circular motion, and this is going to be the last unit in the semester. And like I said before, the fourth unit, Unit 4, is over circular motion, which is basically an extension of Newton's laws, and kind of studies how and why objects move in non-straight lines. So everything we've done up until this point, for the most part, has been involving objects moving in straight lines, either up and down or side to side. Now, we did do a little bit of projectile motion, which involves like a parabola type of path, but for the most part, we've looked at problems involving things moving in straight lines. Okay, so circular motion obviously involves objects moving in circles. So we're going to start off with some definitions here in just a second. We're going to be talking about the difference between rotation and revolution, and then the concept of centripetal force and acceleration, and doing calculations with those things. Okay, so let's start off here, circular motion for A. And like I said, the first thing we're going to look at is some definitions. So please make sure you add these things to your notes. Your last two assignments have to do with definitions and doing really basic calculations, so make sure you pay really close attention and take good notes. Okay, so first things first. An object is in what's called uniform circular motion when it's changing directions with a constant speed. Okay, so in other words, we're talking about something, let me show you. We're talking about objects like this, where the object is just kind of spinning around in a circle, and it's not spinning any faster or slower, and so the speed is not changing. Okay, so that's what's called uniform circular motion, and that's all we're going to be focusing on in this unit. Okay, second of all, we have what's called rotation and revolution, and it's really important that you be able to distinguish the difference between a rotation and a revolution, because you're going to see problems like this on your practice worksheet and your quiz. Okay, so a lot of people think they're the same thing, and they're not. Here's the difference. Okay, it all depends on where is the center of the circle relative to the object that you're talking about. It's all about the center of the circle. In a rotation, the center of the circle is inside the object that is rotating. Okay, in a revolution, the center of the circle is outside the object that is revolving. Okay, so an example of a rotation would be spinning a basketball on your finger. If you imagine, so hold your finger up, imagine spinning like a basketball or a soccer ball on your finger. The center of the circle is where? Well, the center of the circle is inside the ball, right? Okay, because the center of the circle is inside the object itself, that is a rotation. Okay, so a basketball spinning on your finger is an example of a rotation. In a revolution, the center of the circle is outside the object. Okay, so an example of that would be tetherball. Now, if you've never played tetherball, this would be an example of a tetherball setup. You might have seen this before, but not known what it was called. Okay, and so this is tetherball, and these are different little kids playing tetherball, and we're not going to get into how you play tetherball because it's not important. But this would be an example of a revolution. And the reason this would be a revolution is because if you think, where is the center of the circle going to be? Well, the center of the circle, depending on how you hit the tetherball, the center of the circle is kind of going to be along this pole. Right? If you imagine the tetherball going around the pole, the center of the circle is kind of inside the pole. Inside the pole is not inside the ball itself. Okay, so here is the object, the tetherball. The center of the circle is outside the ball. Okay, it's outside the object. That means this would be a revolution. Okay, so that's the difference between a rotation and a revolution. In a rotation, the center of the circle is inside the object. In a revolution, the center of the circle is outside the object. Okay, so take a look, pause it there if you need to add that to your notes. Okay, and then we'll do some examples. Okay, so some really quick examples. It says, label the following as being either a rotation or a revolution. First things first, a hula hoop. Okay, so if you've ever played with a hula hoop before, which hopefully you have as a child, the hula hoop kind of goes around your waist, and then you rotate your hips around. Okay, however, the center of the circle is your body. Okay, that is outside the hula hoop. It's not in the actual plastic of the hoop itself. And so that would be an example of a revolution, just because the center of the circle is not inside the hoop. Okay, now opening a bottle of soda. Okay, when you twist the lid, is that a rotation or a revolution? Well, here's the lid. The center of the circle is right in the middle of the lid, right? Obviously. So that would be an example of a rotation because the center of the circle is inside the object. Merry-go-round. Okay, so if you imagine the merry-go-round spinning with nobody on it, the center of the circle is right here in the middle of the merry-go-round. Because the center of the circle is inside the object, that is an example of a rotation. And finally, the moon going around the Earth. Okay, so here, imagine this is the Earth, and imagine this is the moon. Okay, I cannot draw it all, so bear with me. Okay, and let's say it goes around in a circle, something like this. This is not a great circle, but I'm doing the best I can from home. Okay, so ask yourself, where is the center of the circle? Well, the center of the circle should be inside the Earth. Okay, the Earth is not inside the moon. That means the center of the circle is outside the object, which is the moon, meaning this is a revolution. Okay, so we would definitely say the moon revolves around the Earth, just like we would say the Earth revolves around the sun. Okay, we would also say that the Earth spins on its own axis, and remember, every time it spins around on its own axis, we call that 1 day. Okay, that would be an example of a rotation. Because the Earth spinning on its axis, the center of the circle is inside the Earth, and the Earth is also the object you're talking about, so that would be an example of a rotation. Okay, so as we speak, the Earth is actually revolving and rotating at the same time. Okay, so again, pause it there if you need to. We're going to move on. Okay, and this is basically just repeating the difference between a rotation and a revolution again. Okay, so now let's get to the key concept of circular motion. Okay, and this is important because most objects in real life don't move in a straight line. Okay, most objects move in some type of circular path. Okay, the planets going around in orbit, the wheels on your car, the wheels on your bike, roller coasters go around in some type of circle, merry-go-rounds, race cars go around racetracks in some type of circular motion. Okay, if you imagine how many times you turn in a day, every time you turn, it's like you're moving in a little circle. Okay, you can't live your life only moving in a straight line. You have to turn sometimes, right? And so the study of circular motion is actually pretty important. Now let's go back to Newton's first law. The first law says an object at rest remains at rest, and an object in motion remains in motion at constant speed along a straight line, unless acted upon by net force. Now we said this before, constant speed in a straight line is the same thing as constant velocity. Okay, so in other words, an object will move at constant velocity unless acted upon by a net force, or at constant speed along a straight line. So, true or false? According to Newton's first law, objects in circular motion have a net force upon them. Is that a true statement? Okay, well the answer to the question might surprise you. The answer is actually yes. And the reason is because objects that move in circular motion do not move in a straight line. And if they don't move in a straight line, according to Newton's first law, the only way they can move that's not in a straight line is if they are acted upon by a net force. So the answer to the question is, do objects in circular motion have a net force on them? Yes. Okay. Why? There's two ways to say it. You could either say the object is not moving in a straight line, or you can say it like this. And this, I think you have a problem like this on one of your practice assignments. You could also say that the reason that they have a net force on them is because if you look at the velocity, okay, so this is a ladybug spinning around, okay, it's a little animation I found, and you can see this ladybug kind of spinning around. Okay, now this green arrow, hopefully you can see it okay, this green arrow represents the velocity of the ladybug. Now if you look at the ladybug, and you look at its velocity, if I were to ask you, is this velocity constant or is it changing? The answer is that it's changing. And the reason is, even though the size of the arrow is not getting bigger or smaller, the direction that the arrow is pointing is changing. Okay, so because the ladybug is changing directions, that means it's changing velocity because the velocity, the direction part of velocity is changing. Because the velocity is changing, that must mean there is a net force because of Newton's first law. The only way to move where your velocity is changing is if there's a net force acting on you. Okay, so objects in circular motion do have a net force. Now, this net force in circular motion, we give it a special name. Before we called it F net. For reasons I don't really understand why, but when we talk about circular motion, we don't really call it net force anymore. We give it a special name. Okay, and the name we give to this force, okay, which is really just a net force, is we call this centripetal force. Here's the word right here. Okay, say it with me. Centripetal. Okay, centripetal. Okay, not centripetal, centripetal. Okay, objects in circular motion do have a net force acting on them, and we call this net force the centripetal force. The reason it's called centripetal force is also important for you to know. Okay, the word centripetal, look right here, means center seeking. Okay, in other words, the word centripetal means always going towards the center. The centripetal force always acts towards the center of the circle. Okay, and so as this object is going around in a circle, the velocity is changing direction. The force, the centripetal force, is also changing direction because it's always going to readjust to point directly towards the center of the circle. Okay, now because there's a net force on the object, there's also an acceleration, and so we call this centripetal acceleration. Okay, that's the acceleration of the object, not changing speed, not moving faster or slower, but changing direction. And we call it centripetal acceleration because it's also towards the center. Okay, so let's go back to the ladybug. We saw this before, but the green arrow represents the velocity of the ladybug. Let me stop it there. I'm going to move it a little bit. Okay, so this green arrow represents the velocity of the ladybug. This pink arrow that I just put on, okay, look at this pink arrow. Which way is this pink arrow pointing? Well, it's always changing direction, but it's always pointed towards the center of the circle. Okay, and so the velocity you can see is changing directions. It's always going along the outside of the circle. This pink arrow represents the centripetal acceleration. Is always going towards the center of the circle. And if I could, I would put an option to also put an arrow represent the centripetal force. The simulation doesn't have a centripetal force arrow, but it would be in the same direction as the pink arrow towards the center of the circle. Okay, so again, notice how the direction is always changing, pointed towards the center of the circle. Okay, now do keep in mind that centripetal force is a net force. You never put it on a free body diagram. It's the sum of all of the forces acting. Okay, and so in order to move in a circular motion, one of the forces we've talked about before has to be pushing the object towards the center of the circle. So let me explain what I mean. Okay, here we have a girl spinning a bucket of water around on a string. Okay, now if you were to draw a free body diagram for this bucket, you'd basically have the force of gravity, and because there's a string, you have tension. Now, if you look at these two forces, notice that only one of those forces is towards the center of the circle. The center of the circle is her hand, right? And so, if I were to ask you what force is providing the centripetal force for this bucket to go in a circle, it would be the force of tension. I would say that the centripetal force is provided by the force of tension because that force is pulling the bucket towards the center of the circle. Look at this roller coaster. When the roller coaster is upside down, notice they kind of did a free body diagram already. There's two arrows going down, one for gravity and one for the normal force. You might ask, why is the normal force going down and not up? Well, that's because the surface is upside down. Remember, you always have a normal force when you have a surface. In this case, because they're upside down, the normal force is also upside down. In this situation, if I were to ask you what force is providing the centripetal force for the roller coaster, it's actually two forces, right? Because there's two forces towards the center of the circle. I would say the normal force plus the force of gravity are both providing the centripetal force, because they're both towards the center of the circle. And for the Earth going around the Sun, if I were to ask you what force is providing the centripetal force, think about what forces are acting on the Sun, or are acting on the Earth. The only thing pulling on the Earth is the force of gravity towards the Sun. Okay, and so I would say the centripetal force is provided by the force of gravity. Okay, so these are different situations involving circular motion where we've identified which force or forces, because there could be more than one, which force or forces are providing the centripetal force. Okay, pause there if you need to look at that. Okay, now, really quickly, we're going to do some calculations. Okay, there's two equations you need to know about. Now, remember that centripetal force is a net force, and anytime you have a net force, it's equal to mass times acceleration. Okay, in circular motion, we don't call it net force anymore. We call it Fc for centripetal force. And instead of calling it A, we call it AC for centripetal acceleration. So these two equations basically represent the exact same thing, Newton's second law, F net equals ma, except the second one is for circular motion. Okay, now here is the equation you need to know. Okay, equation number one. The equation for centripetal acceleration is equal to v squared divided by r, where in this equation, v represents the speed or velocity of the object. Okay, that's what we call v, that's measured in meters per second, just like any velocity. And r, lowercase r, represents the radius of the circle, okay, measured in meters, of course, because that's how you measure radius. Okay, so because we have F net equals ma, we can also write the centripetal force equation is the mass times the centripetal acceleration equation, which is v squared over r. Okay, so we don't have a lot of equations in this unit, but here are two of them. One for centripetal force and one for centripetal acceleration. Notice that they're basically the same equation, except the centripetal force equation has mass in it. Now, if you look at this equation, what you'll see is that basically if you move at a faster speed, that means you have a bigger v, it takes more centripetal force to move at a faster speed. Okay, if you've ever, gone driving, sometimes you see these yellow road signs that tell you to slow down, especially when you're like going around a curve. The reason those signs tell you to slow down when you're going around in a curve is because in order to move in a circle, you can't go too fast because otherwise you don't have enough centripetal force to move in the circle. Okay, and that's bad. Then you can drive off the road. That's happened to me before. Okay, and so the faster you move, the more centripetal force that takes. If you look at the equation, the more mass you have, the more centripetal force that takes. Okay, so a small car might be able to go in a circle that a big truck can't at the same speed. Okay, so we've got our two equations, one for centripetal force and one for centripetal acceleration. Okay, pause there if you need to look at that. Okay, and then just really quickly, we're going to do a couple really quick examples. Okay, so here's this picture of the girl with the bucket again. And it says, in the image to the right, a woman swings a 4-kilogram bucket around in a circular path of radius 0.2 meters at a speed of 0.3 meters per second. Okay, so first things first. Okay, identify your givens. 4 kilograms. Kilogram is mass. We've seen that before. They give us the radius right here, so I'm going to label that r. And then they give me the speed, or the velocity, meters per second. Okay, so that's going to be v. Now the first question says calculate the acceleration of the bucket. Which way is it directed? Well, I know which way it's directed. It's directed towards the center. Okay, how do I know that? Because it's centripetal acceleration, which is center seeking. It's always going towards the center of the circle. Now, to do the calculation, all I have to do is do v squared over r. So I take out my calculator, okay, and I do v, which is 0.3 squared, divided by the radius, which is 0.2. Okay, so I'm going to type this into my calculator. Okay, so 0.3 squared is 0.09, divided by 0.2 is 0.45, and that's going to be meters per second squared because acceleration is always meters per second squared. Now, determine which force or forces are providing the centripetal force. We've already done this before in our last example. That would just be Ft for the force of tension. Okay, because we ask ourselves, there's two forces on the bucket. Gravity is going down, okay, and tension is going, guess what, towards the center of the circle, okay, because there's a rope. Okay, so that is the force providing the centripetal force because it's towards the center of the circle. Now, because of that, when it says calculate the tension in the rope, because tension is providing the centripetal force, when it says calculate the tension, that's basically the same thing as saying calculate the centripetal force. Okay, so for this question down here, calculate the tension in the rope, now we're just going to use the equation for centripetal force. M times V squared divided by R. Notice, by the way, only V is being squared in the equation. And that's going to be 1.8 newtons. Okay, and there we go. That is the tension in the rope. And then the last question says, how would the tension change if she swings the bucket around faster? You would say that the tension would, of course, increase. Because if you look at the equation, it's mv squared over r. If you make v a bigger number, okay, that means if it's going around faster, that means the centripetal force is also going to be a bigger number. I talked about that before. Please pause it there if you need to look at that. Okay, and then just one more really quick example. Okay, example 2. Girl sits on a tire swing that is attached to a rope that is 2.1 meters in length. Okay, this is going to be the radius of the circle. Okay, notice radius is in meters. Her dad pushes her with a speed. Okay, for the purpose of this equation, speed and velocity you can treat as the same thing. That's going to be our v. If the centripetal force is 88 newtons, okay, so there's Fc, what is the girl's mass? Okay, now there's only one equation for centripetal force, so it should be really obvious which equation you should be using. Here's our equation. All we're going to do now is plug into the equation for centripetal force and solve. For Fc, I put 88. For mass, I leave that as an unknown because I don't know what mass is. I plug in 2.5 squared for v squared, and then I divide by 2.1. I'm going to simplify. The 88 is fine, but on the right side, what I'm going to do is I'm going to do 2.5 squared, and if you do that, you get 6.25, and then I'm going to divide that by 2.10. Okay, so basically everything that's the number over here, I'm going to simplify. Okay, the mass stays the same. 2.5 squared divided by 2.1 is equal to 2.97619. You might ask, why am I not rounding that? Because I'm going to round at the end, and because this is so close to 3, I want to leave a lot of decimals just so I get the correct answer. So I'm going to divide both sides by this number because it's multiplying my mass. And again, the reason I don't round this number is because I'm going to round at the very end, and I don't want to mess up my answer. Okay, so I do 88 divided by that big old number right there, and I get 29.6 kilograms. And that is the mass of the girl. Okay, just a really basic calculation. Maybe a little more complicated calculation because we have to do algebra for this one. But the equations in this unit are really simple. So pause it there if you need to take a look at that. Please let me know if you have any questions. And as always, I will see you guys in the next video.